Hello, Internet! Hello, Fandom Forward fans and fans of science and magic. Thank you for being here this evening to join us for Magic of Science. We have four truly awesome science creators and communicators joining us tonight. I am super excited to talk with all of them, so we're going to dive in very quickly. But first, just before we begin with our first guest, a couple of quick housekeeping things. Number one, feel free, you're encouraged to use the live chat over here to, say hi to your fellow activists and science lovers, ask questions of the panelists. Just know there's about a 30-second delay between when you post a comment and when we're actually able to see it on the back end. So if you ask a question, give us some time to find it, and we will get to it and share. We also have live captions enabled, so there should be a little CC button around this area. Go ahead and turn that on if you would like to have captions. If for some reason it's not working, please let us know. I don't know that we will be able to fix it immediately, but we need to know for future live streams. But it's been working great lately, so it should be fine. And one last thing I want to remind people of before we dive in with our first guest is not only do we have magnificent, cool science creators chatting with us this evening, we also have magnificent, cool science shirts and merch that are available at our shop right here, fandomforward.org/shop. We have nice t-shirts, we have long sleeve shirts, we have cool mugs that have the molecule for caffeine on it, which I know is very important to everyone. So check those out if you're looking at holiday shopping for some, science-loving friends, or you want to send the link to people to buy it for you, whatever that is. So yeah, stop by the shop, and now it is time for our first guest. Hey!
Hello.
Welcome, everyone. Please welcome. This is Dr. Chanda Prescod-Weinstein. And Chanda, will you just tell us a little bit about yourself and what you study and the cool science things you do on the internet?
Yeah, I'm a theoretical physicist. I'm an assistant professor of physics and core faculty in women's and gender studies at the University of New Hampshire. And I'm also the author of The Disordered Cosmos, A Journey into Dark Matter, Space-Time, and Dreams Deferred. And
Which I just want to tell people that is our book club book for the
yes,
month.
thank you so much.
Yeah, so if you are in the Fandom Forward book club, this is the link. If you're not in the book club and you're like, what's going on? Go there and you can read the book with us. If you are in the book club, be on the Discord. We're reading it all month, answer questions. We're going to have a discussion later in the month. It's very good and exciting. So, sorry to interrupt, but I was very excited about that. Please.
I will never complain about interruptions that involve book clubs, especially ones that are currently reading my book.
Yeah.
So thank you. What else can I say? I do a lot of political and social commentary on Twitter, and my areas of research are primarily focused on dark matter. You might have guessed that from the title of the book. And also I do Black feminist science, technology, and society studies. So I'm particularly interested in how race and gender and sexuality, disability, etc., shape how science happens and what we come to know about the physical world.
Very, very cool. I feel I have admired all your Twitter work for a long time, and am very excited to be learning more about your work, both in the book and this evening. So we're asking all of our guests this evening to explain something in their field that feels like magic to them. So what is that? What are you going to be telling us about tonight?
So should I just get started?
Yeah, go for it.
All right. So I am experimenting on you all because I'm going to be trying for the first time to see how much I can tell you about the awesomeness of quantum mechanics and neutrinos in just a few minutes. So what everybody is looking at here is a visualization that is effectively the double slit experiment. So if you've heard of the double slit experiment, that's what I'm going to be talking about. People who are reading the book, oh dear, this is a bad sign. I don't know what chapter it is, but one of the anti-patriarchy agender chapter opens with a discussion of the double slit experiment. So you can get this in more detail if you're part of the book club. So on the left, what you're looking at, and I'm going to start running. This is a Giphy. It's very exciting. Please ignore the bar on the bottom. So on the left, what you're looking at is a wave, and the wave is coming towards two slits. So you have this yellow line, and you see there are two holes in the yellow line. And as the wave goes through the slits, you see that it gets shaped. And the wave that comes through interferes with the wave from each slit, right? So you see there's wave here, and then they're interfering with each other. And what I want you all to pay attention to is that on the wall, you see this kind of flashing. There are these kind of like hot spots, right? Where the wave seems to be hitting the wall in a way that's more vibrant. So these are hot spots. These are places where you expect the wave to be stronger, right? So this is what happens when you send a wave through two slits. Okay, so hopefully we have some intuition for that. Okay, now what I'm showing you is data taken by Dr. Akira Tonomura. And so these are actually electrons that have been sent through two slits. And so in the first box, you see there are just a few electrons, and they seem to be kind of randomly distributed. Okay, so now in the B box, we have more electrons, maybe tens of them, maybe on the order of 50, 60. Then in the C box, it looks like we have like hundreds, maybe. Mm-hmm. And it's starting to look a little bit less random, right? And so you're starting to see that maybe there are some bars forming, and then you go down into the D box and those bars are starting to get stronger, and you get down to the E box and those bars are even stronger. So what are you looking at? You're looking at wave-particle duality. So instead of just acting like particles and just randomly scattering against the wall when the particles go through the two slits, you actually get this pattern, this interference pattern that looks exactly like that one where the waves were hitting the wall. So this is a beautiful example of the fact that the objects that we call particles also act like waves. And right now I'm surrounded by light. And this is like, for me, the magical part. This was the part that I actually wanted to get to, is we experience light as a wave. But actually, when you send light through one of these kinds of experiments, it lands on the wall like little dots of particles. Mm-hmm. And that's really, you get the combination that you have this pattern, but you also get the particle-like behavior. So it really is wave and particle at the same time. Mm-hmm. It's not one or the other when it feels like it. It's both at the same time. So what's the lesson here? Wave-particle duality means that matter is non-binary. All particles are waves and particles at the same time. So just to kind of get that visual of what we were just looking at, this is particles being sent through a double slit and producing the interference pattern on the wall. So the interesting thing, and again, for people who read the book, you will learn about this. I actually didn't really think about this connection with, thinking about in terms of non-binary until I heard Amrou Al-Qadi, an Iraqi-British drag queen, talk about their identity as a non-binary person. And they were like, well, particles can be waves and particles at the same time. So if particles can be non-binary, why can't a person? This was in an interview with Channel 4 News in the UK. So I can't take credit for the making the point that matter is non-binary, but I'm super happy to reference another person who is, I don't know if you want to say genderqueer or gender dropout. I'm on that spectrum. So that's wave-particle duality. Matter is non-binary. The last thing I want to share. Oh, do you want to ask a question?
No, go ahead. I'm just
okay. The last thing I want to share with you all. that I also think is pretty magical and exciting. So what you're looking at here is the standard model of particle physics. There's a lot on here that I can't talk to you about. If you want to learn a little bit more about it, you can watch my TED Talk. There's a lot out there. What I want people to pay attention to is the green boxes and the top line of the green boxes. Or the bottom line of the green boxes. So the electron neutrino, the muon neutrino, and the tau neutrino. So maybe you've heard of neutrinos. These are subatomic particles. These are fundamental particles. This is every particle on this diagram is all of the particles that we have ever directly seen in the universe. So I work on dark matter. So I have to tell you that that's actually a really small fraction of what's out there, but we're not talking about that today. So
Read the book.
Yes, read the book. The first chapter in particular, at least read the first chapter. So what I wanted to share with you all is that neutrinos are non-trinary. So we just went through matter is non-binary, neutrinos are non-trinary. So what does that mean? So neutrinos, let's say you have nuclear reactions happening in the sun, and that leads to electron neutrinos being emitted. Well, as they travel away from the sun, they will actually oscillate into tau neutrinos and muon neutrinos. And they oscillate in and out of being different neutrino types. So this is called neutrino oscillations. It's related to the fact that neutrinos have mass and neutrinos are non-trinary. And I will actually claim that I'm the person who came up with that way of putting it, inspired by Amru. So I will stop there, and thanks everyone for listening.
Yay. This is very cool. I like that there is so many examples in nature of non-binariness and just things that go beyond our understanding of the way we have categorized everything in the world, all the way down to, it sounds like, the very smallest kind of particles. That this is very cool. What does it mean that if it can be these three things at once? Like, what are the implications of that?
Yeah, so this is actually pretty interesting in part because it's a problem that we know that it actually happens, but we don't actually have a complete theoretical description of why it happens. And this is related to trying to better understand the mass of the neutrino. But as an example of how we know that it happens, we know from our understanding of nuclear physics, and this is why I invoke the sun, we know how nuclear reactions happen inside the sun. And so we actually know how many electron neutrinos should be emitted from the sun. So there was for a long time this quote solar neutrino problem where we weren't seeing the neutrinos from the sun that we were expecting to see. And it's because they were transforming as they traveled to us. And some of them weren't electron neutrinos anymore, and they had turned into a totally different type of neutrino. So we know that it happens. We still don't fully understand that it happens. And I think, it's pretty magical. And, originally when I was thinking about what I was going to talk about, one of the things that I thought I would say is actually for me, one of the best parts of my job is talking to audiences and particularly helping other Black folks understand that the cosmos belongs to us. And so I will just say, actually, when I was in high school, when all of this stuff about neutrinos was happening, I did not think that they were that interesting. And my mom, who's originally from Barbados, was like, neutrinos are the bomb. And it took me decades to catch up with her. She's like very fashion forward with particles. But neutrinos are, in fact, the bomb. They're awesome.
That is fantastic. And your mom sounds awesome, too. Chanda, folks were asking in the chat, like, where can they follow you? But just coming to the end of your time, is there anything you want to just tell people where they can find you, anything you want to plug, etc.?
Sure. So you can find me by just searching for my name and Twitter, and you will find my Twitter account. And you can also find me on Instagram, chanda.prescod.weinstein. So I think, and you can also find me on Substack. So I encourage people to actually, because we don't know what's going to happen with any of these social media platforms. So I'm just chanda.substack.com. You can sign up for my mailing list. And I promise you, I don't write frequently enough, so you will not be overwhelmed.
Perfect. Perfect. Chanda, thank you so much for being here with us tonight. This was really, really, really a treat, and I'm so excited to continue to dive into your book as well. Thank you so much for being here.
Thank you so much for having me.
Yeah. Have a fantastic night. Oh my gosh, my mind is already completely blown, everyone. We're gonna shortly bring our next person. I just want to do another plug for a beautiful Magic of Science shirts. Science is just magic. We don't wait, I'm mixing up the quote. Listen, if you want to know what the quote is, go to the shop link right here, and it'll help you out because it is time to bring on our next guest, who I'm very excited. Hello, Dr.
Hi.
Shenell Tolson. How are
Hey.
you?
I'm good. How are you?
I'm good. I'm excited to be here. So we were just talking about like particle physics, little teeny tiny neutrinos, and this feels right because we're sticking with you and we're sticking small, right? Because
Yes.
yeah.
That was super cool. That was so cool. That was so cool. I'm so sorry about my voice. I'm getting over an illness, and so
Yeah, who isn't these days?
Yeah. So if you can't, let me know if you can't hear me. I'll try to speak really slowly and everything. But
Yeah.
But yeah, happy to be here. So yeah, that was so cool. I was in the back listening, I'm like, oh my God, that's so cool. That was awesome.
Yeah.
Yeah.
I love it. I love it. I'm a science admirer, a science novice, so all of it is new and interesting to me.
Yeah.
Dr. Tolson,
Yeah.
I know that you study cell and molecular biology, but
Yeah.
the people here want to know more about you. So like, what do you study and what do you do on the internet?
Okay, so let's talk about it. So, hi everybody. My name is Dr. Shenell Tolson. I'm a scientist, a public health professional, and I'm an adjunct professor. As a scientist, I work in risk assessments, and that is in reference to dietary and occupational and residential exposures to antimicrobial compounds. So, really, really tiny compounds, and they're antimicrobial, so they're live.
Mm-hmm.
As a public health professional, I specialize in making complex science concepts really digestible and they're usable so that people can understand what we're talking about, right? So SciComm, science communication. And I use that information to help improve health outcomes. And that usually leads to healthier communities, right? And then as an adjunct professor, I teach STEM and allied health courses. So that's what I do.
That feels like you just said, "Hello, I do everything." It's very important and impressive. I love it. I love it.
Thank you.
So
I mean, I think it's cool. I think it's important. I think it's magical.
yeah. Well,
Yeah.
God, improving health outcomes is something that is direly needed at this time. You must feel you
Yeah.
have some level of like, job security, or like need need security. But listen, fun things. So we're asking everybody here tonight to explain something in their field that feels like magic to them. So what is that for you?
Awesome. I can do that because I think so. I'm a scientist, right? So I'm a
Mm-hmm.
nerd, huge nerd, and I'm dealing with antimicrobials and exposures and dietary, all that kind of good stuff, right? So I'm into the science. What I think is really magical is I'm able to use that. Again, I could take really complex science concepts and
Mm-hmm.
break them down to people who may not understand science or get the concepts that we're talking about, particularly when it comes to personal health and public health
Mm-hmm.
directives and why we do certain things, right? People don't really think that there's a STEM background with the directives that we're receiving, especially now. But it's true.
Mm-hmm.
If we understand, what I find is if you can explain something to someone in language that they can hear and understand, they're more likely to one, comply, but two, make healthy behavior changes, better choices, and get better healthy outcomes. That's what I think. And it's working so far. People really enjoy understanding why they need to do something. If you tell someone
Mm-hmm.
to do something, they're gonna be like, well, why do I need to do that? If you help them to understand why they're doing it, they're more compliant and it makes it
Yeah.
easier for them to do it.
That's so critical. So
It
like
is.
what's an example of something you've done that with that you've really loved?
I am so glad you asked that, Katie. So let's use a really, really, really simple thing. Let's talk about non-communicable diseases. Because right now, everyone's like COVID and the flu and RSV. Those are communicable diseases. Those are things you can catch from somebody else. But we also have a terminology called non-communicable diseases, things you can't catch from somebody else, but they still affect your body and the whole system, like diabetes. Diabetes is pretty common and it's non-communicable. And being a part of the African diaspora, that's something that affects us at high incidence rates. We have really large incidence rates of diabetes. And so I find myself talking to people about this a lot. And typically what happens is people don't understand what diabetes is. What they understand is their doctor says, you can't eat these foods anymore because it's bad for you, you know? So, Katie, I have a question for you.
Okay.
Do you think you understand diabetes?
No, I can tell you a cool public health thing that I saw because I had a friend when we were very young developed type 1 diabetes, and her parents bought a video game that we could play where the main character had diabetes, and we had to go around like collecting syringes of insulin, and also like having to watch our levels with the food and everything. So like most of what I know about diabetes I learned from that video game.
Okay, that's cool because that's going to lead into why that makes sense. You said your friend had type 1, so that makes total sense. So let's get into that. So basically, this is how I'm bringing in STEM to help people understand diabetes as a concept, right? So what actually is diabetes? Diabetes is when your body can't regulate its blood sugar. Well, why is that important? Because similar to how cars run on gas, human bodies run on sugar. Does that make sense? So if you want your car to go, you put gas in your car and it goes. If you want your body to work properly, you got to put some sugar in it. And for us, that's food. So no matter what you eat, a carrot or a cupcake, it's got to be converted to sugar because our bodies are sugar machines. So what happens is every time you eat something, again, carrot or cupcake, whatever you eat, your body converts that to sugar. That's your body's fuel that it needs to work and live and play, right?
Yeah.
As soon as you eat something, your body is breaking it down. As it breaks down, it digests, and then it absorbs into your bloodstream, all of the nutrients. Well, as soon as that happens, your blood sugar spikes. Your sugar is going to increase in your bloodstream. Why? Because everything you eat, carrot or cupcake, is going to turn into sugar. If you have a regularly functioning working body, you have a chemical called insulin that's going to turn on and flow into your bloodstream. And it's going to reduce or lower your blood sugar levels so that they are healthy and you don't get overwhelmed by too much sugar in your body. That's how a healthy body works. If you're a diabetic, there's two paths you can go. There's type 1, like Katie's friend, where you don't have insulin being produced at a high enough rate or at all for your body's blood sugar to be brought down to the proper levels, right? And in that case, like Katie was saying, they had to hunt around and find an alternative insulin substitute. So they're injecting insulin into their body. That's type 1. The other one is type 2. Maybe your insulin is producing in your body, but the receptors that are used to receive the insulin, make it work, are not functional. That's type 2 diabetes. So you don't necessarily need an outside source of insulin. You just need something to help your receptors uptake that insulin. In either scenario, the problem here is regulating the blood sugar in your body. And again, no matter what you eat, a carrot or a cupcake, everything converts to sugar. So it's super important that you have insulin function working properly in your body. Let's bring a little bit of STEM into that, right? So if you know what a negative feedback loop is, or if you don't know, I'm going to tell you how that works. And I'm going to use a thermostat as an example. And I'm going to bring in insulin and diabetes in this. Let's say it's wintertime, right? It's wintertime in your house. And you set your thermostat to 72 degrees. That's your threshold. When the temperature drops below 72 degrees, what happens? The thermostat turns on. And so your heat turns on. And it stays on until what? Until your temperature goes back up to 72 degrees. Insulin works the exact same way. It's a negative feedback loop. You eat food, your blood sugar spikes. Insulin is secreted and turned on until you bring your blood sugar back down to the level where it's supposed to be. And then once it's there, it shuts off. So negative feedback loops, again, a basic STEM concept, play a major role in regulating our insulin. If you have type 1, you regulate that insulin by giving a substitute for the insulin your body doesn't produce. If you are a type 2 diabetic, then you're taking oral medications to help your receptors receive the insulin your body is producing. And in either scenario, you are regulating your diabetes. Now, why is this important? Because, again, I'm speaking just from the diaspora that I'm a part of. When we go to the doctor, we hear things like, hey, you can't have certain types of food. And these are cultural for us, right? So a little bit of cultural competency is coming in here. So things that are deeply fried, things that are laden with marshmallows, like candy yams and marshmallows, and lots of potatoes and gravy and meats and cheeses. All of these things, again, no matter what you eat, carrot or a cupcake, are going to turn into sugar. But there are some items, some food items, that carry a higher sugar content than others. And so it may be hard for us to say, hey, you know what? I can't stop eating these foods. But the health information that we receive says, hey, you know what? You can't have this all the time. But if someone understands that whether it's a carrot or a cupcake, it doesn't matter. If you tell them that the sugar content is what's important, they can change the frequency in which they eat those foods and also the quantity in which they eat those foods. You can regulate diabetes in several different ways. It's not always you can't have this, don't eat this, restriction, restriction, restriction. But again, if we can introduce basic STEM concepts, right, simple science, and help folks understand the concepts behind why these things take place, it helps them to understand their disease better, helps them manage it in a much more amicable way, and hopefully leads to healthier behavior changes quickly and over a longer extended period of time. I hope that makes sense, Katie. Does that make sense?
Yeah, it made sense, and it made sense. Folks in the chat are saying like, "Oh, this is an awesome analogy." Like, I get it. Like, it's cool. I can see how that's connecting with people. I feel like that must be such a relief for folks who maybe have been going to the doctor and having this less sort of fully explained and also culturally competent narrative to get to talk to you or to see you online and get it explained in a way that it is very understandable. I've never heard that like heating system metaphor.
Negative feedback loop, a basic STEM concept.
Yeah. But
so you see what I mean? And so that's what I think. And that's the magic of that's what I think is the magic of science. I'm able to take STEM concepts. And so now people can understand what's going on with their bodies. And when they understand, when you know better, you do better, right? So
yeah. And then they go to their doctor and they're like, listen, doctor, I understand that we're having to create a negative feedback loop here because my body isn't generating it automatically. That's beautiful.
Yeah, and we can do it with anything. We can do that. And that's just diabetes. Imagine other simple concepts or frequent diseases people are dealing with that they just don't quite understand. We can just break it down in the language they can understand. Compliance would soar through the roof, I believe.
Yeah.
And that's just my thing. So, and that's what I think is natural science.
It's beautiful. It's beautiful. Dr. Tolson, we're at the end of our time here, but I want to ask, like, where should people find you? Is there anything you want to plug for people to check out before you go?
Yeah, so thanks for having me, Katie. Super excited to be here. Thank you again. If you guys want to keep up with me and what I'm doing, I am on TikTok at ToxNtea. I do science stuff there and other stuff because, it's TikTok. I'm also on Instagram at the Public Heath Bae, BAE. And again, I do gardening stuff, all about public health and science and all kinds of STEM things. I'm also on Twitter at G_protein. So that one's not for kids, though.
You're everywhere, just find the level you want to be at.
There we go.
Age appropriate one. Thank you so much for being here. It was an absolute delight. I hope you have a magical rest of your evening.
Thank you, you too. I'll be watching in the background.
Yay. Thanks,
bye, everybody.
Bye. What a delight. I feel like I understand my body a little bit better, which is fantastic. Quick plug for anybody who's just tuning in. We have marvelous science communicators coming on today. We also have marvelous magical science themed merch. We got cool magic science t-shirts, long sleeves, really cute mugs that I'm going to be getting one and you should be getting one too. So stop by the shop to check that out. And next, we are going, so we talked to folks who are doing teeny tiny particle physics, teeny tiny cell and enzyme work, and now we're switching gears. We're thinking big now. We're going big, climate big, with our next guest. Hello.
Hi, how's it going?
Hi, Miriam. Welcome, welcome, welcome. Welcome here. I know that you do awesome, cool communication around climate, but not everybody else here does. So can you tell me a little bit about what do you study? What do you do? What do you do on the internet?
Yeah, totally. I actually made some slides for that because I will forget what I should say if I don't have those in front of me at all
Perfection.
times. So
Perfection.
We don't need the title slide. That's pretty boring. So hi, my name is Miriam Nielsen. I'm a PhD student at Columbia University and NASA Goddard Institute for Space Studies, which I think is the sneakiest NASA office because it is disguised as the restaurant from Seinfeld.
I was just looking at that.
Yeah.
Cool. I've been to your office before.
Probably, yeah, it's great. Everyone's always taking pictures out, and then I feel like I'm a spy going into a government office. So in this building, I study extreme hydroclimate events. So the disaster movie type scenarios where we've got droughts and floods and fires all happening simultaneously. So my research is not always the most optimistic. To deal with that, I make silly faces on the internet, or I guess technically I have a YouTube channel where I talk about environmental stories that go beyond the headlines and try to create a supportive, energized space for anyone concerned and activated in the climate crisis. Awesome. But even though the results of my research are distressing to say the least, I do want to make the argument that climate science can be fun. That's what I'm going to try to do today, because there's a lot of fun ways to do the research, even if it is kind of a bummer. So I get to mess around with satellite data, and most importantly, I get to play with climate models, which are basically government-funded crystal balls that can show us real and imagined versions of the past, present, and future of our planet. Yeah, so that's basically what I do. And then I
already find this magical. Just looking at that, just looking right there at the crystal ball. I'm sold. What else can we know about this?
This GIF will show up basically throughout the entire presentation because it's my favorite thing to look at. So I guess to get started, I will try to define what is a climate model. The kind of most basic definition is that it's an attempt to replicate our planet's climate, but that's a pretty boring definition because it's just kind of moving words around. So I'm going to break it into two pieces and first define what is climate and then look at models specifically. So what is climate? It's defined regionally. It's the long-term patterns of weather in any given place. So here in the US East Coast, where I am, we have 4 really distinct seasons, and they're defined by temperature. But if you're over on the other side of the continent in California, the seasons aren't quite as distinct, and they're more defined by rain, or depending on who you talk to now, fire. So next up, what is a model? So in this context, it's a bunch of rules trying to replicate that climate and all of the other regional climates of the world and put them together into a model that makes some physical sense. In practice, a climate model is just a pile of code that solves some really scary looking equations. They look really complicated, but models can actually be really simple. My friend Simon Clarke has a great YouTube and Twitch series where he builds his own climate model. He puts it and runs it on a Raspberry Pi, not the old tiny box one, but the new fancy keyboard one, which has a little bit more RAM. So has a little bit of an easier time. But so they can go all the way from kind of small that you could run it on any computer that you own to really big, which requires a massive supercomputer, racks and racks of servers, and entire teams of software engineers and scientists to build and develop. And that's like the one I work on at NASA GISS. And it's trying to replicate the interconnected parts of our climate system. So at the most basic, a climate model is looking at the energy that's coming from the sun and then the thermal energy that the Earth emits back into space. From there, you can add more physics, you can add the ocean, you can add chemistry, you can add trees, and you can add bees and people. And eventually you put together something that looks like our planet. You got the continents in the right place. You got the ocean currents moving in ways we expect. There's the big rainfall band around the equator, and it's actually rainy, which is harder than you think, despite it being a pretty fundamental part of our climate. And then we can add in greenhouse gases, and we get warming in believable ways. So this is, the replica Earth in our crystal ball. And that's where things start to get fun, because honestly, what a climate model is kind of the most boring part to me. What it can do, though, now that's where things get fun and exciting. So from this big pile of code, you can flip a switch and suddenly you have a supervolcano that can end an ice age. Or you can flip a different switch and suddenly there's no more wind on the planet. You can use that to figure out the theoretical limits of wind power. We can burn down all the forests and see if that affects droughts, or we can reforest a desert and see how that changes rainfall patterns.
Huh.
But before I get in too much trouble with my boss, the point of these climate models is these very, very expensive climate models is not to just create these weird and apocalyptic scenarios and see what happens, although that is definitely something that we do a lot. We've built these things because while we understand a lot of the physics, the chemistry, the biology in our world on their own, we don't really know how everything works when it gets smashed together into the reality of everything else. And that's what climate models are really, really good for. So we can ask a computer to solve these really complicated equations that we couldn't solve on our own, and then try to incorporate everything we know. We're pulling stuff from geochemistry, we're pulling stuff from astronomy, we're pulling everything we can and smashing into these big, massive computers. And then we can ask for a simulation of the Earth with twice as many greenhouse gases and see how that might affect other systems, like how the increasing temperature that melts ice sheets and changes ocean surface temperatures impacts global rainfall patterns, or what drought looks like in California versus the Mediterranean. Because all of these pieces are interacting, and unless we can actually look at what's going to happen, it's going to be really hard to predict the future, since I don't know about a time machine that exists yet. Now, because we are on the internet, wherever this recording ends up, more than likely someone's going to get their typing fingers ready and say that all climate models are wrong. And I will be the first to say, or not the first, like the thousandth to say, yeah, they're right. Not all climate models are correct. If a computer simulation was able to perfectly reflect the Earth's climate, one, I would be out of a job, which wouldn't be that bad. But two, I'd be very worried that we were in the Matrix.
Mm-hmm. A constant threat that I worry about as well.
Constantly. So my PhD advisor, Kate Marvel, likes to say, we don't want our climate models to be perfect. We want them to be useful. And the ways that climate models are wrong can actually teach us a lot. She uses this example. So if we take a look at some of the most up-to-date, sophisticated global climate models that we've got, they're very good at simulating the Earth's temperature and look very similar to what we've observed. So the observations of the black lines and all those colorful lines are some of these up-to-date modern climate models and the change in temperature since the 1960s. So they're all kind of, squeezed together. They're all roughly in agreement. But if we project that out to the end of the century, obviously we don't have observations for that, but the models start to spread out a lot and we get a lot of uncertainty. They don't all agree. Some of them say that New York, where I am right now, is going to look an awful lot like Florida, and others are literally more chill. Everybody agrees that things are going to get warmer. That's the trend. That's the physics. When you add greenhouse gases in the atmosphere, temperatures rise. But how much warmer, we still don't totally know. And so that's kind of the murkiness in this crystal ball metaphor, if I keep stretching it out, because every climate model has to make a bunch of decisions on how it models. So specifically on tiny processes. And by tiny, kind of reflecting back to, it's not the same tiny as subatomic particles that other folks have talked about, or molecular cells. We're talking Earth scale tiny, not butterfly wings or any of that other stuff. Although dust is pretty important and that's quite tiny, but I don't study that, so I can't speak to it too much. But apt for this metaphor, clouds happen to be one of the biggest tiny problems. The Earth has a lot of clouds at any given time. Clouds are covering about 65% of the Earth's surface, but clouds are created by tiny pieces of ice and dust particles. We know a lot about the creation of clouds, like an individual cloud. We can create clouds in bottles. We can do all sorts of cool stuff, but there is no computer on Earth powerful enough to model every piece of dust that could possibly become a cloud. So climate modelers have to make decisions on how their models are going to create clouds. And kind of the same thing, getting from the atmosphere down to the surface. This is just a generic slide from some of my research. We have the same problem on the land. If you look at the historical period, this first half of all these plots, all of the models are very close together. This is all of the average of them, super close together. But as soon as you start to go in the future, it gets wider and wider and more uncertain because the models don't agree anymore. And that's one of the most difficult problems of understanding what's going to happen in the future, aside from things are going to get warmer, but what's it going to do? However, what we do know, we don't know the future. We do know the decisions the modelers made, and they have to publish the equations they're using. They have to talk about what observations they've included and what assumptions they've made. And from that, we can start teasing out possible stories for what could happen in the future. Whether, a really hot model is saying, oh, that's actually because this mountain range isn't going to have any more snow melt, and therefore you're not going to have as much runoff to water your crops in the fall, because all that came down is rain instead of snow. And you start to be able to tell different stories. I'm getting a little bit off track. Let me see if I can figure out how to get this back.
It's all interesting.
I'm just going to kind of wrap it up a little bit and just say, like, the best part of climate models is that they're not actually crystal balls, sort of undercutting my metaphor. They're not mystical orbs that we can kind of stare at and define our future. For better or for worse, they can't tell us if we're going to stop using fossil fuels or write policy to protect from disasters. But they are built on physical, unchangeable properties of how fluids flow and how heat moves. And their results are all around us, from farmers' almanacs that use the predictions of El Nino to headlines describing how floods or droughts will be more likely in the future in some places, to every single evening news story that talks about the future of wine. And I think that's pretty neat.
This is very cool. So, listen, number one question we've gotten in the chat is, can I play with this myself? Basically, is there anywhere that climate models are accessible to the public like this, that people can play around with it?
Yeah, totally. Cool. So, I mean, they kind of range in complexity. So, I mean, Simon's model, if you want to look him up on YouTube, his is on GitHub. You can just straight up download it. It's very small compared to other ones. There's the Community Earth Systems model, CESM2, that you can just download and run on your own machine as well. It's a little bit more complicated and has a bit of a learning curve. All of the models that I work with, which are part of the Coupled Model Intercomparison Project, or CMIP, are available for download. They are very large files, though, I will warn you in advance. But they are downloadable and you can play with all the output. A slightly easier way to play with the output is with the most recent IPCC report. The UN released an interactive atlas. So if you type in IPCC AR6 atlas, you can get a really fast web version where you can kind of look regionally, what are the projections looking like in the future.
That's cool. For anybody who didn't catch all of that, great news. We're on YouTube. You can just go backwards a little bit and find all of that again. This is fascinating stuff. Does experimenting with this, does it give you sort of like more dread or more hope, or somewhere in the middle?
I think somewhere in the middle, I would say.
That's fair.
Here, I'll just like, I don't do that anymore. It is nice. I get some sense of like knowing what is going on or what could happen. I find that personally very helpful for me to just kind of like, if we know, we can prepare. A lot of my outside of the climate model work I do is based in disaster response and emergency management. And so recognizing the possibilities of these events that could happen means that we can channel money and people power to protecting against those. So that's kind of the positive spin. It's like, climate change is going to bring a lot of scary stuff, but it's not any quote unquote new events. Like we've seen hurricanes, we've seen fires before. We know how to respond to them if we take the time to care about the people impacted. So knowing what's coming lets us prepare.
Yeah.
Theoretically.
Yeah. Well, yeah, sure. I like it. I feel similarly, and this was fascinating. This was fascinating to watch, both because it was very interesting and also because it made me realize I didn't know what a climate model was before this moment. It's just one of those moments where it reveals like, oh no, I thought I understood the world. This was very, very cool. We're coming to the end of our time. I want to thank you very much for being here and ask you, where should people find you on the internet, and any special projects you want to plug?
Totally. I am basically everywhere on the internet as zentouro, except for on TikTok because someone parked that. And so now I just don't make TikToks because of it, because I'm petty. But anywhere else you can find me as zentouro. I very occasionally make videos. Turns out continuing my video making and doing a PhD is harder than I thought it would be. So there will be one eventually again. But that's probably the place that the community tab on YouTube is the one that feels the least like it's going to disappear tomorrow. So that's where you can find me.
Speaking of being prepared. Beautiful. Miriam, thank you so much for being here tonight and showing us really, really cool GIFs and also educating us about the climate models. Thank you so much.
Thanks so much for having me.
Yeah, have an incredible, magical night.
You too.
Yeah, thanks, Miriam. Really friggin' cool. Really friggin' cool. Oh my god. All right, listen. You've been here now. You know what's happening. Coming up next, me telling you to buy our shirts. We've got beautiful Magic of Science. Long sleeve, short sleeve, mugs to fill up your cup if you want to stay up late and playing with climate models. You just like douse yourself with caffeine and go nuts. Um, speaking of staying up late and doing shenanigans, I believe our next guest is here.
Hello,
Hi.
hello. Love the segue. That was
Thank you.
very impressive.
It's I don't know anything about science, but I know a lot about segues. Darrion, thank you so much for being here
Of
this
course.
evening. So I know you on the internet as Lab Shenanigans, but not everybody here knows you. So could you tell us a little bit about, what do you study? What do you do on the internet?
That is a great question. Speaking of segues, I have a PowerPoint presentation that I can. Oh,
Beautiful.
bam! Whoa!
Seamless.
So I studied at the University of Texas at Austin, and I double majored. I double majored in biochemistry and theater. And I actually want to ask you, Katie, are you a theater kid? Were you a theater kid?
Is it that obvious?
Yes, you were, huh? Yes, I can tell.
I was once told by one of our volunteers that I host our live streams with big community theater energy, which I take as a compliment.
Literally, when I jumped on, I was like, Katie is a theater kid. I know it, and I just have to ask her. I have to ask her. So
I've been perceived.
I feel seen. So I studied biochemistry, and I also worked in a lab. Here's me looking really derpy, my hair, working under my grad student, and then I also was in a play where I played as a squire, and here I'm becoming a knight. And then after I graduated, like every college graduate, I entered my quarter life crisis period of what do I want to do? I have 2 useless degrees. So as a filler period, I worked as a research tech, and we moved into the new lab space, and I did sagittal sections of mouse cerebellum and stained it, and it looked nice. So we hung it up. And in the middle of me working this lab for a couple of years, it was very stressful, and I turned to social media as my outlet. And I just made a lot of like relatable lab content. At the same time, I made a lot of educational biochemistry, biology content by personifying or portraying specific mechanisms or certain systems that we see or we learn in science concepts. And so that was the birth of Lab Shenanigans. That's how I adjust the slides. And so at the same time, I applied to several PhD programs, and I got into my dream PhD program, but I turned it down because I was like, to make my story arc sound more impressive, let me reject grad school. No, this was just blowing off, or not blowing off, this was blowing up. And and I was like, I want to do this. And so I started to pursue Lab Shenanigans on these different social media platforms. One of the platforms that I'm leaning in on is YouTube. And one thing I love to do is look at a trend or phenomenon and try to either explain the science of it or go into depth and explain more science about it. So, so here is here's a thumbnail. One of the pictures that I a video that I made about Asian flush. If y'all don't know, it's when us Southeast Asian people, when we consume alcohol, we turn red. So throughout this whole video, I explain the science of Asian flush while I'm inebriated. And so, yes, it is a hot mess, but it's also very educational. And so that is on brand with me, messy and educational. And so and one of the things concepts that I just am that I am obsessed with is convergent evolution. Now, for those that do not know what convergent evolution is, It's when different species evolve over time that are not related. However, they adapt to their environment, their surroundings, and they develop very similar traits. And so if you were to look at them, you would think, they might be related, but they're not. So here's an example where something evolves into, I don't know the exact animal, evolves into a dolphin, and then ancestor two evolves into a shark, and they both, they can swim. And so you would think that, oh, maybe the dolphin or the shark are related. Similarly, like how bats can fly, birds can fly, some insects, but they're not related. They all can fly. So that is an example. And I like how a lot of video games are picking up on science concepts. And one video game that I want to focus on is Pokemon.
Oh, cool.
So for those that are familiar with Pokemon, the Pokemon on the left is a Diglett. It is in the first generation Pokemon. And the Pokemon on the right is a Wiglet. Okay. In the new Pokemon game, Pokemon Scarlet and Violet, which will actually be released this Friday. And one of their trailers, they introduced this new Pokemon, and the description was like something like, this Pokemon looks like Diglett, but they're not related. They just grew, they adapted, or they evolved in the same environment. And I thought, wow, that's so cool. And Diglett and Wiglet both evolved into Dugtrio and Bugtrio, respectively. And I just think it's so cool. They look very similar, right? So, one would say, oh my gosh, these Pokemon programmers are getting lazy with the designs. And I say, no. I think Pokemon programmers are science communicators. I think they are just trying to be more realistic, and they're trying to bring science concepts to the Pokemon world. And one specific type of, or one example of convergent evolution that blew my mind a couple of years ago was carcinization.
Oh.
Have you heard of it?
I think I can guess from the picture. I have not. The word makes me think like of carcinogens, and I don't think that's what you're hyped for.
You want to hear a funny story? I had a lab dinner last week with my lab, and I was telling them how like I gave this talk quite often, but I've been calling it crabification. And they're like, Darrion, I think it's called carcinization. I'm like, I don't think so. And so this is probably the first time that I'm giving a talk online where I gave it the correct name. I know.
What an honor. Thank you.
See what I do for y'all? I actually do my research this time. So I almost started again. Carcinization is the concept that several crustacean or species evolved to look like crabs. That's the key word, look like crabs, okay? Now, within this family, here's a family tree, starting with the Miura, branches off into two different families, the Brachyura and the Anomura. Now, the Brachyura are what we call the real OG crabs, okay? They've been crabs since day one. They are not fake crabs. They are not fake imitation crab meat. They're the real deal. And you're probably asking, what is a crab, Darrion? That's a great question. Well, crabs, they appear to be round and flat, and their legs are spread around their abdomen, if you will, okay? And then the other family, the Anomura, are the fake crabs. The fake crabs, meaning early on, a couple of million years ago, the early ancestors looked like lobsters and shrimp. But then more recently, and by recently, it's like a couple of million years ago, they adapted or they evolved to look more like the modern crab. All right. And so you're also asking, like, why did they evolve to look like crabs? Well, it was during this period, the Jurassic period, where reefs were just expanding, and a lot of animals were specifically ocean animals were just diversifying, and it was more favorable, more suitable for them to have smaller round bodies and run away from prey. And I kind of want to explain how they evolved over time. So here's a schematic of a lobster. I didn't draw this. I took it off of Google. Oh, I just realized I did not cite this Oh, get it together, Darrion.
Get him.
I
Get him,
know.
people.
Roast me in the comments. Someone say cancel Lab Shenanigans. And so
Mostly they're just saying they prefer crabification
I know
right now.
it's more intuitive. You would understand carcinogen. You probably think that like, oh, someone died for inhaling a carcinogen. No, and it sounds scary.
It
sounds
does.
Scary.
It does. Blame the Latin speakers from
I
long ago.
know. Cancel Latin people. That's it. No, just kidding. Y'all heard it from Katie.
I'm getting the hook.
Katie literally said cancel Latin. Oh my god, I can't believe you wrote
Said
that.
Latin speakers who are mostly all dead at this point.
So this is actually a lobster, but just pretend this is an early ancestor, of a lobster. And so the tail or the plion, but I like to say the plion. It just sounds sexy, like French, the plion, the tail. Over time, it grew shorter. So here is my amazing Photoshop skills. Bam! Okay, and then here is the carapace. And the carapace over time grew flatter and wider. So kind of like a BBL for the lobster, if you will. Bam, bam. And the legs are more dispersed around to allow it to crawl. Now, this schematic probably didn't do it justice, so I got a figure from the paper. And I actually cited this time. So I'm not canceled anymore. So like I said, the carapace has evolved to appear rounder and flatter. The sternum, specifically the legs in the sternum, rather than aligning in the middle, it is more, I guess, around the carapace underneath the sternum. And then the plion is flatter and is tucked underneath behind the sternum. And this has been so very favorable for these animals because having a longer tail or a longer plion, they can get captured by predators. Having a flatter carapace allows them to hide or burrow under the sea ground. And having legs more spread out allows them to travel and run away from their predators. So to end this presentation, I wanted to end it with a very inspiring quote that I saw on Twitter. This is the ideal male body. You may not like it, but this is what peak performance looks like. Thank you, everyone, for attending. This is wonderful. I love this. I love this.
Beautiful. If you have questions about crabification, please
Yes,
drop them in the chat. This is I love the comparison to Pokemon, and I 100% agree with you that it was the Pokemon designers just being like, we're bringing in real science.
Oh yeah, I'm so for real. I'm going to make a YouTube video explaining why Pokemon has been so good within the past couple of years because they are bringing a lot of science concepts into the game.
Yeah.
For those that do play Pokemon, I'm talking about like the Alolan region Pokemon. So they're like these Pokemon, but in specific regions they have different variances. So like I can't think of one like a Pikachu. There's like there's this region called the Alola, I think the Alola region, and there's like a Alolan Pikachu variants where it looks more like I'm not explaining it very well, but
it looks a little different because
it's the concept of speciation. Okay, you think of like the turtles on the Galapagos Island, how they adapted to that environment. So it's very similar to that. Pokemon has been doing that with every generation, every Pokemon game.
That's really cool. Darrion, it was such a delight to have you here and to have you be canceled and then uncanceled and then cancel me and inspire us about crabs and Pokemon. If people love this, and it does, we're getting a lot of thank yous, many crab claw claps to you. Lots of Pokemon facts. If people are into this, so like where can they find you? Where can they find you on the internet? I know everywhere, but refresh us.
That is a great question. unlike your previous speakers, my handle on everything is Lab Shenanigans on TikTok, Instagram, Facebook, uh, uh, Twitter, OnlyFans. I'm kidding. I don't have an OnlyFans. Zynga, MySpace, Tumblr, everything. Lab Shenanigans.
Zanga. Find me on Friendster.
On real.
That's fantastic. Thank you so much for being here, for showing us the ideal male body, and for closing out our night with just absolute shenanigans. I loved it.
Thank you so much. This was so fun. I love you, Katie. I love
Yay.
you.
Have a fit from one theater kid to another.
Oh, yeah.
Have a fantastic night, Darrion.
Thank you. You too.
Yay.
Alrighty. Bye, y'all.
Bye. Goodbye. Thank you, everyone, for being here this evening. Like, I learned so much. Okay, I learned about cells. I learned about particles. I learned about the climate. I learned about crabs. And now I have to go Google crabification. No, that's not the word. I bet if I Google it, I'll find more Darrion videos, and that'll be perfect. Yeah, remember, if you loved this, we had another one on Saturday, so you just watch this whole one. Go to our YouTube page. You can see everybody we talked to on Saturday. They were equally awesome. It's holiday shopping time. You know it. You tolerate it, love it. Go here and buy some magical merch to help support our campaigns that are going to be coming in 2023, which is sneaking up on us like a little lobster sneaks up on a crab evolution. Thank you, everybody, so much for being here tonight. Oh, one last plug. Two last plugs. I lied. If you go to fandomforward.org/magicofscience, we have a toolkit full of fun science experiments that you can do at home. If you have kids at home, it's a great fun thing to do with them. If you are just a kid at heart, it's a great fun thing for you to do. So check that out, download that. And also, reminder that our first guest, Chanda, has a book that we are featuring as part of the book club this year, this month, The Disordered Cosmos. Check that out. If you're not in the book club, this link has instructions on how to join us. If you are in the book club, swing by the Discord, answer the questions that we're talking about there, and get excited for our end of the month chat about this awesome book. Thank you. I love you. You all are magnificent. Go forth and be scientific and magical, and have a wonderful evening. I'll see you next time.